Dear Professor Heckman, Professor Sims, Director Ken, the organizing committee's distinguished guests, ladies and gentlemen, good morning. On behalf of Academia Sinica, I would like to welcome all of you. We are honored to have this opportunity to host the 2014 Asian meetings of the Econometrics Society. And I would like to express my appreciation to the organizing chairs, Professor Kam Hong Ken, 简景汉所长 Professor Long Fei Li, 李龙飞院士 Professor Ping Wang, 王平院士 and Professor Xin Kun Peng, 彭信坤前所长 and the Institute of Economics for the effort in launching this great event. Also of equal importance, thank you for your participations. It is your participation that makes this conference a true success. For the purpose of promoting econometrics research, Asian meeting held by Econometrics Society provides a great platform for worldwide scholars to exchange their research ideas. The conference has great success in the past 5 years, thanks to the previous hosts, National University of Singapore, University of Delhi, Korea University, University of Tokyo, and Singapore Management University. This year, we are very honored to have 2 Nobel laureates in economics to deliver the keynote speech. Professor James Heckman from University of Chicago and Professor Christopher Sims from Princeton University. We also have 15 invited lectures by other leading scholars in various fields in economics, including a lecture by the president of the Econometrics Society, Professor Manuel Arellano. In addition, we have parallel sessions covering a broad range of issues related to economics. I believe you will be inspired and learn the latest development in economic research during the 3 days conference. In addition to academic interactions, we also have social events to facilitate networking and to show you Taiwan's rich culture and warm hospitality. We start with the welcome reception tonight and followed by a conference dinner tomorrow. Hope all of you could join our social events. Besides, I'm a historian. I encourage you to visit our museum, the Museum of Institute of History and Philology, just 5 minutes walk from these buildings. The artifacts exhibited in that museum is mostly excavation from Shang Dynasty. That is many 15 tombs of the Shang kings, all the excavation or stored in Academia Sinica. And the largest amount of ochre bone in the entire world also stored in that museum. And many bronze vessels, many other artifacts, precious things, very precious. Most of them are several hundred years before Homer's age. And stone carving, and all kinds of things. Yeah, so it's a very precious collections. Most of them was borrowed by Palace Museum for almost half a century. But due to the former directors of the Institute, Du Zhengsheng, our former Minister of Education, when he was director, he asked the Palace Museum to return all of those precious things to Academia Sinica and to remodel that museum. So you are, many years ago, that's I'm talking about 15 years ago, the events of 15 years ago, strongly urged Palace Museum to return the precious collection Palace Museum borrowed from Academia Sinica. And during that negotiation, Professor Du, director of the Institute, was suddenly announced to be the director of Palace Museum. But that is already, negotiation was already undergone. So the precious collection finally returned to academicians. So you are very encouraged to go to visit that museum. It is open today, because I was director of that institute before, so I know it's open today. Free. Very precious. You will never disappoint it. Anyway, with this 3 days intensive workshop, we hope you would have a productive and enjoyable stay in Taipei. And thank you for your attention. Thank you.
Thanks for Professor Wang's impressive opening remark. Now, please welcome our session chair today, Professor Ray Sheng Tsai, to chair the session. Please welcome.
Good morning. It's early in the morning, but I think we are all here for the main purpose. Is the important section, the presidential address. I don't think we need to say much about Professor Manuel Arellano. I'd like to mention a few things just to remind you his important contribution. He's newly elected honorary member of the U.S. Academy of Arts and Science recently. And also, if you look at some of his important contribution, just cite one example. You look his name under the Google search or the Google Scholar. One of his papers got cited more than 14,000 times. The second one is more than 6,000 times. So that two of the paper, you can give you idea about how important his contributions are. Okay, then let's welcome Professor Arellano.
Well, let me begin by thanking Academia Sinica for hosting the meetings of the Econometrics Society, and thanking the organizing committees for putting together a very impressive program and organizing a wonderful conference. It's very warm thanks to all of you. There is a long tradition of Econometric Society meetings in Asia. Next year, it will be the 50th anniversary of the first Far Eastern meeting of the Econometric Society. And this occasion is keeping up long and prestigious tradition that we are very keen on expanding and preserving. Thank you. So let me move to my presentation. Okay, right. So this is work that belongs to macro-motivated empirical inequality studies using micro-panel data. This type of studies have evolved alongside the shift in macro from study of the dynamics of aggregates to the dynamic of individual distributions of outcomes. Two major themes there are the sources of household income inequality and the measurement of consumption insurance against income shocks. Now, the purpose of my talk is to review newly developed econometric methods for nonlinear models with latent variables that are then applied to the study of the dynamics of income and its effects on consumption over the life cycle. This is a talk on applied econometrics methodology. First, I'm going to discuss a Markovian permanent transitory model of household income, which, as you will see, reveals nonlinear persistence of unusual shocks on PSID data. Then I will discuss the nonparametric identification and estimation of consumption rule, an age-dependent consumption rule that is a function of assets, permanent income and transitory income. We are able to do this partly thanks to the availability of rich panel information on consumption, earnings, and assets in the new waves of panel data, the PSID. And you will see this framework leads to new measures of consumption insurance against earning shocks, which can be calculated from short panel data. In terms of the econometrics, these are nonlinear dynamic models with latent variables. The latent variables here are the earnings components, permanent and transitory earning components. Identification relies on nonparametric techniques. We built on recent work by Hu and Shenag and Willem. And then the estimation methods use flexible parametric models that combine quantile modeling and linear expansions in basis functions. Our estimation method relies on a version of the stochastic EM algorithm that I developed in earlier work with Stéphane Bonhomme. So this is going to be an econometrics of quantile regressions, sieves, and simulation-based computation. The outline for the talk is in 4 parts. First of all, I will describe the model, nonlinear permanent income model of consumption, permanent transitory income process, and a consumption function. Then I will talk about identification. I want to focus on simple cases that hopefully I will manage to get the message across that what we are after is a methodology that let us produce empirical quantities in broader context than the particular examples that we consider. Then I will talk about estimation, this simulation-based sequential quantile regression calculations, and then some empirical results to conclude. All this is joint research with Richard Blundell at UCL and Stéphane Bonhomme at Chicago. Permanent transitory income processes. An income process is the context that I want to talk of them, representation of the uncertainty about labor income in future periods that households face when deciding how much to spend. The standard approach, standard at least since Friedman's work, decomposes uncertain future income into a permanent component and a transitory component. This is the canonical income process that has been the backbone of the literature for many years. So there Y is log income of household I at age T. Here I want to emphasize the life cycle aspect, so T is age. And this is a net of cohort effects. And there is a permanent component, this is eta IT, and a transitory component epsilon. And the permanent component is a random walk in the canonical model. There are lots of extensions of this in the literature. Fixed effects, stable autoregressions, moving averages, age-specific variances, lots of things. Difficulties. Well, a major difficulty in estimating uncertainty from earnings data is that one can't rule out the possibility of overstating uncertainty because of unaccounted heterogeneity, or because what the model labels as a shock has been foreseen by consumers. So About omitted fixed effects, well, this canonical model includes a fixed effect, which is the initial permanent component, is the starting point to the random walk. But the model without random walk with less persistent shocks and heterogeneous growth is hard to distinguish from the canonical model, yet it's a very different description of uncertainty as perceived by households. To be clear, I mean, a fully unstructured distinction between unobserved heterogeneity and individual dynamics in a finite horizon panel is not possible. One has to take a stand. Superior information, earnings data alone can't conclusively identify to what extent, if any, agents are able to anticipate the stochastic variation in the estimated process. Other difficulties, well, choices versus shocks. Risk measures from earnings histories alone are necessarily crude, since they abstract from income variation due to endogenous labor choices rather than exogenous shocks. If we have data on employment and wage histories of household members, then one could consider a joint model with a more detailed set of shocks than the canonical model. But their progress has been held back, partly because additional labor variables are discrete events, and these are hard to combine with continuous variables in a convenient statistical framework. But more fundamentally, it is difficult to examine a detailed menu of shocks without simultaneous consideration of a comparable menu of sequential household choices, since future exposure to a particular type of shock may be contingent of previous choices. Here, a delicate choice to make by researchers is to what extent you want to provide micro foundations for those shocks. As I said, the perspective here is deliberately crude, so I'm staying at the income level for the purpose of this talk, where it's kind of a very macro, big lens perspective here. Now, this is our emphasis here. See, the mainstream approach to earnings dynamics fits this canonical model, or some variant of it, to covariances of household income panel data. And the one point I want to make is that the focus on covariance restrictions is overly restrictive. Canonical model rules out asymmetric persistence and nonlinear transmission of shocks. There is for sure scope for progress on measuring risk using additional data, shock histories, subjective expectations in combination with realized income data, but also using income data in a more exhaustive way, looking at the distributions rather than stopping at the covariances. I'm going to try to illustrate that going from an econometrics of autocovariances to an econometrics of flexible distributions is flexible, is feasible, is practical, has the potential to reveal richer aspects of risk. So I'm going to discuss a permanent transitory model that replaces the random walk component with an unrestricted macroprocess. In this model, different shocks may be associated with different persistence, since they interact with the lagged earnings component. For example, unusual shocks like job or health loss may not only have a large direct effect on income, but may also wipe out the memory of past shocks. Macro disasters could have potentially large effects on savings behavior, and there is a well-established literature on this, but they are so unlikely that they are statistically elusive events. In contrast, disasters at the micro level happen all the time to some individuals, and therefore the dynamic consequences may have clear-cut empirical content. Now, consider a cohort-specific process for the log labor income Y of household I at age T, net of deterministic part given by the composition that we had before, but now this eta follows a general first-order Markov process. If you call tau the conditional quantile of eta given lag eta, and this is this Q function, then we can represent the process in this way. This U is the innovation, and which has uniformly distributed on 0, 1, given the history of the process. And here eta 1 is left unrestricted, and this Q is age specific. So there is a different Q for each age. The time component, epsilon, is independent over time and has 0 mean. Now this model allows for nonlinear dynamics of earnings. These derivative effects or average derivative effects, rows, expected rows, measure the persistence of eta t minus 1 when hit by a shock U of rank tau. In the canonical model, this rho is equal to 1 for all histories and values of the percentiles. In contrast, in this setup, the persistence of eta may depend on the magnitude and direction of the income shock U, right? So stochastic volatility and asymmetric persistence are both allowed into this framework. Anticipating things later, just to give some practical content to this, let me show you these couple of pictures. These are calculations of average derivative effects of rows for simulated data from the canonical model to the left, and from simple nonlinear model, caviar type of quantile autoregression to the right. And the simulations come from these models, these two models, fitted to PSID data. And the horizontal axis, you have different percentiles. So close to 0, you have very bad shocks, and close to 1, you have very good shocks. And the vertical axis, you have the derivative effects, and the canonical model, you have this is flat, is not unity here, because this is being done for the observed data, so it's lower level. But interestingly, on the right, you can see that persistence is much higher for normal shocks, say, but persistence decreases very significantly for unusual shocks. And this happens in an asymmetric way at both ends of the distribution. Now, I'm going to skip this. One can, of course, calculate conditional interquantile ranges as measures of uncertainty, measures of conditional skewness based on the quantiles, and one can also calculate shocks that are not just ranks, as these U's are, but are of a magnitude comparable to permanent income. And this can be constructed in a variety of ways. One way is as explained in there. So moving into the consumption function, there is literature that seeks to identify the links between income shocks and consumption from the joint covariance structure. This goes back to the work by Hall and Mishkin, the early 80s, and important contributions along the line in Deaton and Paxson, and more recently Blundell, Pistaferri, and Preston. Blundell and co-authors interpret the degree of transmission of income shocks to consumption growth as a measure of the extent of insurance opportunities open to households. A simple version of their model for income and consumption growth is what you have there. The first equation is just the canonical income processing first differences. The second equation is a linearized consumption growth equation in which these pi's are associated with insurance coefficients. 1 minus pi's are the insurance coefficients for permanent and transitory shocks, right? This is basically their framework. Now, of course, this relies on double linearization argument, first of the Euler equation, then of the budget constraint. And this has limitations because there are aspects of consumption responses that are nonlinear in nature. And besides, I mean, if we are considering a nonlinear income process, one would expect this to produce nonlinear responses of consumption to income shocks as well. So I want to discuss a consumption model that helps document nonlinear responses to earning shocks. And what I consider is an age-dependent nonlinear function of assets and the persistent and transitory earnings components. This is this GT function, which has as arguments assets. These are all in logs here. The etas, the epsilons, and then there is this extra error term, which you can think of as a tail shifter that increases marginal utility. It is normalized to standard uniform here and is regarded as independent of assets and income components. So that's the consumption function. It allows for interactions between assets, age, and the earnings components, hence providing a rich picture of consumption insurance. Assumptions about stochastic assumptions about assets. Well, the initial assets are independent of future income shocks, both permanent and transitory, but crucially, they are arbitrarily dependent of initial permanent income. This is important because these initial assets, this initial permanent income is not the beginning of anybody's life. These are just the beginning of data collection in this problem, right? And aside from these, period T assets are independent of lag etas, lag assets beginning in T-2 and lag epsilons beginning in T-2, given assets in the previous period, consumption in the previous period, and income in the previous period. Now, these stochastic assumptions about assets, this is of course consistent with the standard accumulation rule of assets in a model with one single riskless assets, but still, I mean, could be empirically strong, and we have considered extensions of this beginning. At this point, I just want to stress that this consumption function as a policy rule is fully consistent with what would be the standard life cycle model of consumption and savings with partial insurance and heterogeneous agents. I have put together a slide to remind us of this, but there is nothing in particular there. Now this is just maximizing expected discounted utility subject to the accumulation constraint. And the information set contains permanent and transitory components as separate components on which households can form probabilities. And so the consumption rule that comes out from that kind of problem, and there are a variety of borrowing constraint assumptions, is broadly of the form that I have described. But let me emphasize that the purpose here is not to estimate this particular model or any other particular model. The purpose is to provide an empirical framework for assessing the qualities of a model like this and other models, and possibly suggesting modification to other models. And insurance coefficients, these are consumption response to e-test. These averages are taken with respect to this error term in the consumption function, and then the psi is the consumption response to transitory shocks, right? And this you should think as functions of assets, permanent income, and transitory income. I'm of course using permanent income and transitory income deliberately in the original loose sense of the word. Of course, here this permanent income is just the permanent component of the income process. And the marginal effect of a deadening shock U on consumption, then you can calculate by combining these phi component with derivatives with respect to the permanent component of the income process. This is a slightly strange object because these are derivatives with respect to the rank form of the permanent shock. If you want the derivative with respect to a form of the shock in units comparable to the permanent income, then you would add an extra term to an expression like this. So identification. The discussion of identification relies on injectivity assumptions, and these are by now common in the literatures of non-parametric instrumental variables and measurement error methods. Special case of injectivity is completeness. Completeness in econometrics appeared initially in the non-parametric instrumental variables model. So let me recall that problem because I will use it as an intuition for where identification of the consumption function that I've just described is coming from in a moment, right? So this is, let's see. Right? So this is the IV equation. Y3 is the outcome, Y1 is the endogenous explanatory variable, and Y2 is the instrument, right? And the object that we want to identify is this function H. And the H solves this integral equation, right? And this is a data object. This density is also a data object. Now, there is a unique solution to this integral equation if the density of y1 given y2 is complete, or if the operator that has this density as kernel is injective. This is, to some extent, this tautological statement is just saying that the dependence between y1 and y2 is rich enough that we can back up the entire form of this H function from this integral equation. But this is a nice way of thinking about the problem because we can connect with standard intuition from linear instrumental variable problems. In fact, in a discrete situation where this becomes a probability mass function, this situation is equivalent to a full rank condition on the matrix of conditional probabilities, right? Now, identification of the income model, I'm going to do this rather quickly. I have discussed this in previous talks, and this very much relates to work by Daniel Whelan. His setting is formally analogous to our income process with 3 periods. What he does is to study a class of non-parametric panel data models with measurement error. And what he gives conditions under which the distribution of epsilon 2, with t equals 3, there is an epsilon 1, an epsilon 2, and an epsilon 3. And he gives conditions under which epsilon 2 is identified. These conditions are essentially completeness conditions on the distributions of y2 given y1 and eta2 given eta1. which essentially mean in our case that there is dependence, there is a rich form of dependence between eta 1 and eta 2. So the reason why there is identification here is first because there is dependence in the permanent component, and secondly because this dependence is limited in a Markov fashion. Okay. Now, applying this result to each subpanels of 3 waves, we can identify epsilon 2, epsilon 3, epsilon 4, and so on, right? And having got these epsilons, because of independence among these epsilons, we identify the joint PDF. And having got the joint PDF of the epsilons and the joint PDF of the income data by the convolution, we can identify the joint PDF of the etas, right? And having got the joint PDF of the etas, then we can identify the distributions of the etas given the etas minus 1s, which are our Qs, right? These are the permanent component in the income process. But casually looking at this argument, you might think, well, if you can identify the joint distribution of all the etas, why do you need a Markov assumption? Well, you actually need the Markov assumption to identify the epsilons in the first place, right? Okay, so let us move to assets and consumption. I said that it is very important in this context to allow for unrestricted dependence between initial assets and initial permanent income. So where is the identification of this coming from? Let's see. So this is the data object, again, the distribution of initial assets given income. This income here is the entire time series of incomes for a given household, right? And given our assumptions, these can be expressed as an integral of the distributions of the initial assets given permanent income and the density of the permanent income given the y's. Now, this equation is formally of the same structure as the instrumental variable problem that I showed a moment ago for a given value of A1, right? So doing the mapping, eta 1 is the endogenous regressor and y is the vector of instrumental variables in this problem. So identification of the distribution of initial assets given eta 1 is going to require completeness of eta 1 given y, right? In the IV context, of course, y and eta 1 are observable. Here, eta 1 is not observable, it's a latent variable. But the distribution of eta 1 given y is identified from income data. This is why we can argue in instrumental variable terms about the identification of this problem. If you wish, the kind of thinking in instrumental variable terms is a distributional non-parametric counterpart to what would be the familiar thinking in linear panel error invariable models, as in the work of Wilkes and Hausman and others. Okay, so let us move to consumption. Now, let us first do the consumption function in the first period. I'm going to do first the first period because the argument for identification of subsequent periods will proceed by induction. And so in the first period, this is the distribution of consumption and assets given income. So this should be in the data. We can do, we can do complementary data sets at some level, but not others. For example, in the previous slide, I said that this is identified from the income process. So the informational content here in the PSID context could come from the long PSID, right? As this is fed to this equation, even if the information for assets only comes from the more recent new PSID. Okay, but here we need, our data is, joint data on consumption, assets, and incomes for given households. And this is basically what our assumptions provide. And this is the object of interest. This is the consumption function. The consumption function is the quantile function for this probability distribution. Okay, this is what we want to identify. And then what we are considering is an operator, a linear operator that uses this as the kernel, right? And if this operator is injective, then this component will be identified. And since this is identified from my previous slide, the conditional density of consumption given assets and permanent income and initial income will be identified. Of course, there is observed income here, but this is equivalent to having epsilon 1 instead of y1 in there, which is what we have in the interpretable consumption function, right? So the intuition, again, is that here y2, y3, up to yt are used as instrumental variables for permanent income in the first period. And therefore, if you want to state the requirement for identification or the relevance condition, if you like that sort of language, we need completeness in y2 up to yt of the density of theta 1 given y1, y2 up to yt. It's completeness in y2 up to yt because y1 now is kind of a control variable in this instance, right? So now to conclude the argument, I want to, where am I? Yes. Before I move on to conclude the argument, let me say a word about the injectivity of the operators. If the etas and the y's are normally distributed, injectivity just requires non-zero covariance between eta 1 and eta 2. Providing primitive conditions more generally is challenging, and there is an active literature that is looking into this. But considering subsequent periods, what I do here is to now consider this is the data, this is the joint density of all the consumptions up to period t, together with all the assets up to period t, given all the y's, right? All the time series of y's. And this depends on a data component, which is the distribution of assets given past assets, past incomes, and past consumptions, and then an integral on the objects that we are interested to determine, right? And of those components, we can break them down into the one that corresponds to the consumption function in period t and the previous ones. All the previous ones, I call this kappa t, and this kappa t becomes the kernel of the operator in this instance. So given injectivity of this operator, then identification of the consumption function in period t follows. Having got identification of the consumption functions for previous ages. So there is an induction argument there. And again, the intuition is that lag consumption and assets, as well as lags and leads of income, are used as instruments for the eta t's in this instance. Okay. This is a simple situation. What other situations can one consider? Well, we can use similar techniques, and in fact, in the work with Richard and Stefan, we do so. We can consider advanced information. We can consider habits. This would be modifications of the consumption function. We could consider a version of the consumption function in which instead of assets, a cash on hand measure is included if one is willing to make the assumption that cash on hand can be measured sufficiently well. And the extension to household and observed heterogeneity in earnings or consumption, however, is more challenging. For example, heterogeneity in discounting or preferences, or heterogeneity in the Markovian transitions of the ethers. We have also pursued these extensions. I said at the beginning, and I want to emphasize that point, there is no free lunch here. One has to take a stand. We cannot have unlimited and observed heterogeneity and free dynamics here. But we can allow for some fixed effects. This is a version of the consumption function which includes a fixed effect that enters non-parametrically in the problem. This is a scalar fixed effect, right? And this scalar fixed effect is assumed to be arbitrarily dependent to initial assets, initial permanent income. One can elaborate the previous arguments to establish identification there if T is sufficiently large. We've been able to prove identification in this context if you have at least 6 waves. Okay, so let me move to the data and the estimation strategy that we use. The words about the new PSID, which is only new relative to the very old one, and since 1999, the PSID reports detailed data on consumption expenditures of non-durables. This is about 70% of all non-durable consumption and asset holdings. This is key for being able to do this exercise on this particular data set. In fact, most previous work of this kind was based on food consumption or imputed consumption data. Asset holdings here are the sum of financial assets, real estate, pension funds, car value, net of mortgages and other debt. The expenditures that are in the consumption measure include food, rents, health, utilities, car-related education, childcare. The main items missing are recreation, alcohol, tobacco, and clothing. Rent expenditures for homeowners are imputed. In this, we followed recent work by Blundell, Pistaferi, and Supporter. This is not ideal, but that is what we are doing so far. Consumption and assets are residuals using the same set of demographics as for earnings as a crude way of equivalizing. Current results are based on a balanced sample of 714 households who are participating, and married male heads aged 30 to 65. So in a sense, these are households to whom nothing very major is happening. The empirical specification for the quantile function of ethers, given ethers -1, we specify a sieve quantile model. And these phi's are a dictionary of functions, and we proceed in similar terms for the quantiles of initial eta and initial epsilons. And these are also functions of age. We want to be very flexible age-wise in this specification, but we have so far done a pooling across cohorts, which allows us to identify the distribution of the epsilons non-parametrically at all ages between 32 and 63. For consumption, we proceed similarly, except that we enter nonlinear, we enter additively the residual in the consumption function. This is not essential, but this is what we've done so far. So from that point of view, the consumption function in this instance is not a quantile regression, but nonlinear least squares regression in latent variables. But again, we use similar sieves. Implementation, we followed Wei and Carroll modeling the coefficients, the quantile specific coefficients as piecewise linear interpolating splines. And this is a convenient choice as the likelihood function is available in closed form in this way. And the tails we treat separately. We model the tails as exponential. In practice, we take 11 knots, and the phis are low-dimensional tensor products of Hermite polynomials. Further 3 for income, or further 2 in the consumption function for age, assets, and permanent income. The estimation algorithm. This is, as I said, an adaptation of techniques in my earlier work with Stefan. We proceed in 2 steps. We don't want to estimate jointly income and consumption there. I mean, estimating jointly income and consumption has distinguished history in the literature, but what we want to do here is different. We want to commit to a measure of income risk and take this to consumption data. So you cannot have both ways. Since the income process is identified on income data alone, we proceed sequentially, and we estimate the income process first, and then conditional on these estimates, we estimate the consumption rule. And how do we proceed? Well, the call theta, the income-related parameters, call mu, the consumption-related parameters. This is the posterior density of the etas given income data, and then given this density, the parameters in the income process. For a particular quantile, minimize an expected integrated check function, integrated with respect to the posterior density of the etas. Simulating from this posterior density is easy because the joint likelihood of etas and y's given h is available in closed form. Likewise, for the consumption parameters, well, this solve an optimization problem. They minimize expected integrated square residuals integrated with respect to the posterior. This is another posterior density of the etas, but now conditioned on the data at this level. Consumptions, assets, and incomes and ages, right? And then in compact notation, we can put together all the restrictions that we have in the problem. This is for the income process, and then we use stochastic EM algorithm, stochastic as opposed to simulated in the sense that we produce new draws every iteration, as in the work of Nielsen, and so we follow 2 steps until convergence of the Markov change. In the first step, and in the E step, we draw from the posterior given candidate for the thetas, and for doing this we use Metropolis Hastings, and then in the M step we do a bunch of quantile regressions. Right? And this is critical for this being a practical procedure, because at the M step is non-likelihood, is method of moment based. But then this is very good for being able to handle lots of latent variables, right? because essentially we run linear quantile regressions on a bunch of imputed data from the previous draws, we could rearrange if there were crossing the quantiles, but actually there is no need to, because in drawing from the posterior there is an automatic rearrangement that takes place. Okay, so this is the way we proceed. We do something similar for consumption. So actually the statistical properties of the procedure are well understood, not for the method of moment situations, but for the likelihood situations, in situations where the approximating model is the true model, thanks to the work of Nielsen on the stochastic EM algorithm. So what we have done in our work is to adapt his results to this method of moment situations. In our other work, we have also dealt with special cases in the non-parametric vein when the number of nodes goes to infinity together with sample size and establish consistency. But there we only have partial results in the literature. There is now a fully worked theory for this type of model, if you want to think of it as a strict implementation of a non-parametric estimator as opposed to a flexible model. And now to conclude, let me take the last few minutes showing you some results. Now this is persistence measured for the income process. This is rather interesting. So let me tell you what this is. So in this axis, you have income shocks. This is a very bad shock. This is a very good shock. These are also percentiles. But these are now percentiles of eta t-1 of permanent income previous year, right? And so round here is a very good history, and round here is a very bad history, or low permanent income, if you wish. And so what happens here, if you have a very good shock, and you have a bad history, the very good shock wipes out to some extent the memory of this bad history. The persistence here, is less than 0.8. And similarly, if you have a very good history and a very bad shock, this can have devastating effects. And but around the central range of shocks, for bad histories and bad shocks, persistence is much greater. Shocks, the shocks that comes, more of the same, is very close to 1. So over the very central range, the canonical model would not be as bad. This is now in terms of fit. This is now on observed data. This is predicted by our model. Fit is reasonably good. And this is same as before in the data, and this is what would be predicted by data simulated from the canonical model estimating on PSID. A rather different picture of the persistence, rather flat. And the densities of the permanent component is fairly normal for the permanent income, very normal for transitory income, in line with other things in the literature. Now, consumption. The consumption responds to permanent income by assets and age. This is quite interesting as well. So this is this axis here. You have asset percentiles, and here you have age, right? So on average, the the consumption response to permanent income is about 0.4, so more than 50% of permanent shocks seem to be insured in that sense. But this is on average. See, if you are an older household, then you are more insured than if you are a younger household. There is a life cycle aspect to it. And if you are rich, you are almost fully insured. Right? If you are rich and old, the effect of those shocks is rather tiny. Responses to transitory shocks are essentially nil or negative, in line with other results by Blundell, Pistaferri, and Preston, and sometimes negative, which is somewhat puzzling. Consumption responses to observe incomes by assets and age to check the fit of the model. This is data, this is the model. In this dimension, the model does pretty well. Another dimension which it doesn't is the dynamics of consumption. This version is one that doesn't have a fixed effect in consumption, but that's about it. So the rest of the discussion includes some calculations of impulse response functions, which I'm going to speak in the interest of time. So let me just conclude. This is a framework that is intended to be practical and feasible for acquiring information about the relationship between income and consumption's inequality over the life cycle. It leads to new empirical measures of the degree of partial insurance. Hopefully it will be useful to assess the suitability of existing life cycle models and help guide developments of new models. Further work is needed to accommodate richer forms of unobserved heterogeneity and asset processes in the existing framework. Thank you very much.
We have a couple minutes. Quick questions. Any questions?
You were stressing age dependence, but in some sense, a lot of these consumption functions were all just not so much the age dependence, right? You didn't really develop that in your final results. But you think that maybe you get rid of any kind of age dependence per se once you condition things like assets and income levels and so forth, right? Microphone. Oh, okay. So I'm saying you were conditioning, you talked about age dependence a lot. But a lot of the results in literature are partly a result that people aren't conditioning very much on things like the asset stocks and various other kinds of histories that individuals have. I'm just curious, not only in your conceptual framework, but just in your empirical results, when you condition in this general way, do you find much age dependence? I mean, there might be in a finite horizon model, things like, discounting and so forth. But I'm just curious empirically how you...
Yes, that's right. Then once you condition on assets, age dependence in the consumption function doesn't come out as strongly as it could in other contexts. Here we are emphasizing the life cycle aspect, that we could reprocess this kind of econometrics in business cycle context. That would be a very interesting different type of application. Formally, the way we have organized the data analysis here, the processes are non-stationary age-wise, but fully stationary calendar time-wise, right? There is no room for calendar time the way we are dealing with the analysis. Here we are taking one cohort, and then we are following that cohort over time, and think as time as age.